TTL Computer 2. Today we'll be taking a look at some updates to our backplane design, as well as just to take a look at a status on our build out and testing on our backplane as well. Now, so we're looking at our a 3D view of our backplane, and unfortunately, it was just 2 days after I submitted our backplane to fabrication that I found out that we are in fact not caring for something that we need to care for, and that item is relevant to our power circuit here, and if we flip over to I'm going to flip over to our circuit diagram now. All right, and this is what we were just looking at in our 3D view. And this is our barrel connector for our 5 volts coming in. And then we have our resettable fuse, right? And that's our main VCC for powering the board. Now, this fuse is caring for some of the items that we need to be mindful of in our power design. And this is really addressing overcurrent situations in our board, and does kind of take two flavors of that. And one is just when if we plug in a new board, and it's just the nature of the board. It's just the boards require a certain amount of power based on the components on them, draw a certain amount of power from the power supply, and we need to ensure that that doesn't go over a certain number. And for us, that's going to be 6 amps, and we're using the 6 amp fuse here just for that purpose. So we just don't want to add extra boards that go over the 6 amp limit, because that's our design limit. So that's one variety of overcurrent, and the more dangerous variety of overcurrent is a short circuit, right? If we have a trace or whatever, so for some reason we have a failure in a trace, or a failure in a component that results in a direct path to ground, that's going to make the current shoot up really high, and we want to protect from that, because in a situation like that, overcurrent, we could damage a component, we could damage, even worse, we could damage a trace, and we don't want that to happen. So those are the two varieties of overcurrent that we're aware of, and we're protecting for with this resettable fuse. And so we haven't really talked about what that resettable fuse is, but um, what that is essentially a variable resistor, and the resistor changes its resistance based on the temperature of the resistor and the material, and it's better known as a thermistor. And this is a special kind of thermistor that's called a PTC thermistor, and the PTC stands for positive temperature coefficient. And what that means is that the resistance on this thermistor goes up as the temperature increases of the material or the resistor. So that's pretty much what we want in a resettable fuse. So as long as the current is under 6 amps, this fuse is going to have a very low resistance. But as the current starts to approach 6 amps, it's going to start to heat up. And shortly after 6 amps, it's really going to reach its tripping temperature, and the resistance on this is going to go very high. So that effectively shuts down the current. And then if we remove the power from the circuit, this would cool down, and again the resistance would go low, and you could plug in your circuit again, but you would obviously look to rectify the problem there. So those are two forms of overcurrent that we're protecting from: just the circuit drawing over 6 amps, just as the nature of the components, and second is if there's a component failure or a short circuit. Now, this is the third case that didn't know about beforehand, and that's causing us some problems now, and that is inrush current. Now, I've never designed or built a circuit anywhere near this large, right? This is going to have, eight boards in the computer, including the backplane, and it's going to draw something like 4.5 amps. That's a lot of current. And again, something I've never designed or built to. But what happens is, we have a lot of capacitors in our circuit on all the different boards. And those capacitors, when the power supply is initially applied, those capacitors are effectively a short to ground. And what happens is that the current, when you apply the power, the current draw goes very high, right? Until the capacitors charge, and then the current would come down. So that peak, that in current, that current surge to charge the capacitors and charge the circuits is called inrush current. And that current spike can be very high and could be very damaging, again, to components or to worse off even traces in our circuit. So what we want to use for now, let's say we're taking this out, we're taking this resettable fuse out, and we're going to plug in a different kind of thermistor now that's going to address the inrush current. And this is going to be an NTC thermistor, or a negative thermal coefficient resistor. And that works just the opposite of the PTC thermistor. As the temperature rises on this thermistor, the resistance goes low. So what happens is this is going to have an 8 ohm resistance when the power is just turned on. So that's going to limit our current to something about a little bit over a half an amp. And so that will allow the capacitors to charge slowly up to the operating voltage. And then this is going to start to heat up. And as this heats up, its resistance is going to go down to very nearly zero and is going to be transparent. So this works again opposite from the resettable fuse. The resettable fuse goes up in resistance as the temperature goes, and the inrush resistor thermistor goes down as the temperature goes up. So now we have a problem. So what I think I'm going to do is I'm not going to use the resettable fuse. Our circuit board's already designed, is already manufactured. What I'm going to do is I'm going to use the inrush resistor thermistor here instead of the resettable fuse, and because that's really the more important thing. The resettable fuse is really just an outlier condition, right? We don't want that to happen. We don't want to ever reach 6 amps, and we don't ever want to have a short circuit. But this inrush current is going to happen every single time we power up the computer. So that's something that we definitely want to, right? That's the normal occurrence. We definitely want to protect ourselves from that. So my plan is to use the inrush thermistor in place of the resettable fuse, and then when the time comes and I build an external power supply, we will either use the resettable fuse in the power supply, or I'll just use an inline fast blow 6 amp fuse. But that's my plan. So we are going to we're going to use this spot here for our inrush thermistor rather than our resettable fuse. Okay, so let's take a look at our backplane. And as you can see here, we still don't have our main DC barrel jack soldered in yet, nor do we have our inrush thermistor soldered in yet. So we're still waiting on that to arrive. But luckily, what I've been able to do is we have our little 5-volt out header that I'd put it in for testing, and we're actually going to use that to power the board until we get our inrush thermistor soldered into the circuit. So we have some patch cables here that we're using, just tapping into power here, extra power here on the header. And so just giving us some signal lines that we can set up the signals as we need them. And I got these nice long patch cables that are female on one side to attach to our headers, and male on the other side, so we can use with the breadboard. Okay, so we have our address lines set up to be using address hex 2010, which is what we need for our hex display. And we also have our write signal is already patched in to be enabled, but the U clock signal is floating low, and we're all set to power this up. Now, since we don't have our inrush thermistor, what I'm doing is bringing up the power slowly, so we don't have that inrush current situation. So we're kind of being a manual thermistor here. All right, so our board is powered up. So we see our hex display is at 0, 0. And I said our write signal is already asserted. And what we're going to do is we're going to assert the U clock, bring the U clock high, which is the update signal, right? So we already have the address lines are patched to 2010. And our data lines are, these are floating high. If you remember, we have pull-ups on the address lines and pull-ups on our data bus. So right now on our data bus is FF, but that's obviously not being clocked into the hex display. But what I'm going to do now is bring the U clock high, and we'll see here that that's going to clock in. That should clock in what's on the data bus, and it is. And we see there's the FF. Okay, so I'm going to just leave that U clock signal high, and what I just have is a little patch line here where we can. This is low, so we can see that changing the data bus will change the hex. We'll reload the hex display. Now, since the U clock signal is high, it's just continually updating the hex display, right? Because the signals are high to load. All right, so what I'll do here is, let's keep that in there. I'm going to remove the U clock signal. All right, so that's back down low again, and we can see that the data bus was latched in. Okay, and then what we can do here is, as another test, is I'm going to take out A15. So that is, we're no longer matching the 2010 on the address line. And I'm going to bring the U clock back high. So the data bus right now has FF on it, but you can see that that's not being clocked in because our address has been changed. And we'll put this back to 2010, and we see that the FF got clocked in. Okay, so this is all working correctly. All right, so again, the U clock is asserted, and we can see that whatever's on the data bus, the hex display will load whatever's on the data bus. So let's take our write signal low. We unpatched our write signal, so this should not update the display, right? Because we require the address to match, and we address U clock to be high and the write signal to be high. So that's all behaving correctly. Now, that's not what happened in the beginning when I did the first round of testing. So what I saw when I did the first round of testing was, even after I removed the U clock signal, the hex display was still updating, right? So I was kind of getting, right, I was getting this behavior. Whoops. get the right signal back patched in. All right, our right signal's in there. So even though I removed the clock signal, the U clock, right, the hex display was still loading. So I'll take the U clock out now, and we see the hex display is not loading. Now, so what was happening was it would continue to load after I removed the U clock signal. The hex display would continue to load what was on the bus for a time. I determined that it was only for a time, and then it kind of would drain off. So what I used a logic probe and kind of looked at the U clock signal down here, and I'd bring that high, and then it would be remain high for a little bit. So what I determined was that because of the capacitance in the board, the pull down values were not low enough. So we were using 2.2K pull downs for the active high signals, and this is the reason why I'm using these expensive these expensive resistor arrays in the DIP package, was so that if I needed to change these pull up and pull down values, which I had lots of trouble with in my TTL computer, my last computer project, had a lot of problem getting the pull down values right, which is why I use these packages. So I popped out the 2.2K resistor networks, and I put in 1K resistor networks, and which obviously pulls those signals low with a lot more force, let's say, and that cleared up the behavior so that the signals are going high as soon as going low rather as soon as we remove the patch signal. So I'm a little concerned about that. I'm still have concern that it's working fine now with obviously these low frequencies with the manual frequencies. I'm concerned about that capacitance that we've seen in the board with the higher frequencies, right? The 1 megahertz clock frequency that we're going to see with our clock card. So we'll have to wait and see how that goes. But if we have to, I think 1K for the pull downs is pretty low. But if we have to, we could go lower, there if need be. But I said I think the 1K pull downs are such a pretty strong pull down. So hopefully we should be okay. So this is just a flavor for how the testing went. I'm probably going to, next round of testing now is going to be when to start testing the cards. And when I test the cards, I'll probably go back to patching in our testing jig to inject signals. But I'm not 100% sure about that, but I'll see how that goes. It starts to get to be a lot on my bench here. But that will be my next thing to do. Is I'm going to look at the signaling on the clock card, and then we'll be looking at our control card. And then I'm going to be, my plan is to execute again, a portion of the test plans that we used with the testing jig will be repeated on the backplane, and for each individual card is my plan. And it probably won't be the complete test plan, just enough to validate, validate the backplane, that all the signal lines on the backplane are operating correctly. So I think that's it for today. Good progress. So I said, this was one of the issues. I thought I mentioned in my post that I thought I found another small issue. I thought that this was not. I have these two ground and two VCC and ground patch points here. When I tested it, I didn't yet have the header in, and I was testing the signals off of the resistor network. And that was the issue for seeing what I saw, is because it's the header here, not the resistor network. It's the header here that's connected to VCC and ground. So that in fact is fine. So, and then one minor stupid issue is A14 here is not labeled correctly. It goes A12, A13, A15, and A15. So stupid little mistake. But other than that, we're looking okay. So the main issue is going to be is the thermistor here, the inrush versus the the fuse, the resettable fuse. And again, I have concerns now about these pull downs needing to be 1Ks, but we hopefully will be okay. So that's it for today. Until next time, thanks for watching.